Okay, for the last little bit, what we're going to do is we're going to show you how to distinguish when they're all mixed together, because let's face it, that's the hardest part. If I tell you what kind of reaction it is, or if they're isolated to only one type, it's pretty easy to figure it out. But when they're all mixed together, it's just like writing formulas. That's when it starts to get tough, and you're trying to figure out what in the world am I supposed to do next. So for this movie, what we're going to do is we're going to fill out the part of that homework packet that you have that has a flow chart. And we're going to do it in bits and pieces. I can't fit it all on the screen, and so you'll see what it looks like when it's completed. But this is basically going to just go through a little bit at a time. And so we're going to keep up with the sections just by starting at the left side. When you use the flowchart, when you're trying to figure these out in homework or quizzes or tests, it's tough. I mean, this is probably one of the tougher chapters we do all year because it combines so many different things and there's so much reading, interpretation going on. It's tricky. And so the first question you want to ask yourself when you're looking at these chemical equations, you're trying to read them and interpret them, is what are the reactants? Are they an element or are they a compound? And how many do I have? Because that tells you so much if you know how to go from there. But that's the first step, is you have to be able to determine where you're going. Okay, so based on the answers to that questions, you can fill out the chart using the slides that follow you. So if you see one compound, boom, all by its lonesome, that tells you it's a decomposition reaction. And what it's going to do, at least for my classes, is it's going to break it down into the elements from which it is made. And what you want to do is you want to watch out for what I call the Brinkelhoffs. Okay, those guys, when they are being produced, what they will do is they will all come in doubles. So for example, if you had Ni3, and I know we used this example in the movie, it breaks apart into the element. It is one compound. That tells me it's decomposition. It's going to break apart into N and I, but neither one of those, when they are elements, exist as N or I. When they exist as an element, they are diatomic. You need to include that. And these are the hardest ones to catch in decomposition, is trying to catch the diatomics. Oops, gosh, don't do that. Undo that. Hit the wrong button. Okay. If you see a reactant where there's only two elements, I need to slide this over a little bit, I think. There we go. Only two elements. That tells you it's going to be a synthesis reaction. And in a synthesis reaction, there's only one product. And the product is found by dropping and swapping charges, if it's ionic. If it's molecular, I'll give you the name. So to give you an example of this, oops, let's go back, sorry. If you had aluminum plus sulfur, okay, aluminum's a metal, sulfur's a nonmetal, you're going to drop and swap charges on that, and you're going to get this. Okay, but if I gave you that, there's no way to know because they're two nonmetals. You can't drop and swap those. So I would say nitrogen trifluoride. And I would give you the name, and you would have to write NF3 based on the name. Tri means 3, nitrogen without a prefix means 1, and then you would balance to make it work. Okay? If you see this, which is called a hydrocarbon, remember Z can be like 0. Okay, it can be just C and H, and it reacts with oxygen. It's called a combustion reaction. Be careful. Okay, these look like single replacement because it's an element in a compound, but you won't see oxygen on that activity series. That's a big clue. The products are CO2 and water, always. Okay, if you see an element in a compound, that tells you it's single replacement. And in a single replacement, what you're looking for is you're looking for the element to replace inside the compound. Okay, the element's going inside and something's going out. Okay, use the activity series. Remember, it has to be higher on the series as an element to be able to replace. Otherwise, it's no reaction. Okay, the products, if there is a reaction, will be a new element. And again, watch out for your Brinkelhoffs. And drop and swap for the new compound. Okay, now if you see two compounds as reactants, it could be one of two things, and you kind of have to distinguish between them. There's two different versions of it. If it's an acid base, one of the compounds starts with H plus and the other compound ends with OH minus, and the products are always water and drop and swap for the remaining stuff. Okay, but you have to recognize them. You have to be able to look at it and go, oh yeah, I forgot. H is start acids. That's an acid. Is this a hydroxide? Yes, it's an acid-base reaction. Then double replacement is the other kind. And in a double replacement, you just have two compounds. Now, one of them could be an acid, or one of them could be a hydroxide, a base, but not both of them. If both of them are acid, one's base, then you have acid-base. But double replacement, what happens is the cations trade places, and you're going to use solubility rules. You're looking for a solid, and you're going to drop and swap for everything. Okay, this is what it looks like. I know it's really, really small. I know it's really hard to read. But like I said, identify the reactants as elements or compounds and how many you have. And that will tell you how to fill this out. Okay, most of the products, if they are compounds, are going to be drop and swap. Let's do some practice, though. All right, so you're looking at this and you're like, oh crap, everything's thrown together. What do I do? So you want to look and identify first what type it is. Okay, so I'm looking at this and I see a compound and I see an element that tells me single replacement. And then I'm going to look on my little activity series, because with a single replacement, that's where I'm looking. And I notice that sodium's near the top, which means it's going to kick the aluminum out all by its lonesome. And it's going to form Na with Cl, and they're both a 1 charge, and so it's NaCl. But I do need to balance this by putting a 3 here and a 3 there. Okay? Then I look at this one, I think, okay, one compound all by itself makes it decomposition. It's going to break apart into the elements of which it is made. Sulfur is not diatomic, but oxygen is. So I'm going to break it apart into the elements, and I'm going to balance it. Put a 2 in front of the SO3. And now I see 2 elements. When I see 2 elements, I recognize it as synthesis, which means I'm going to drop and swap charges on Na and O. Na's got a 1 charge and O's got a 2 charge, so I get this. And so I need to balance this by putting a 2 here and a 4 there. Okay, I'm looking at this, and I think, at first I see oxygen, I think element, right? But then I see this big organic hydrocarbon over here, and I think, oh, wait a minute, no, this would be combustion. CO2 and H2O. And to balance it, you put a 2 here and a 3 there, and then you count up your oxygens and you wait, oh, odd number, double this, double that, double this. Gives me 8 plus 6 is 14, make that a 7. Okay? Now down here at the bottom, I'm seeing 2 compounds, and that's when I have to go, okay, wait a minute, pause. It's an OH and an H. And it's going to do the same thing a double replacement does. The Na and the H are going to trade places, but technically this is an acid base, and I'm going to have H with OH, which is water. And I'm going to have the Na and the S drop and swap charges, Na2S. To balance this, I put a 2 here and a 2 here. Okay. Last one, again, compound and compound. Very similar to the last one. It's got an OH in it, but this is not an acid. Okay. It's a double replacement reaction, even though it's got an OH in it. Na and Fe are going to trade places, so I'm going to have the Na go with the NO3. It's a plus charge. NO3 is a 1 minus charge, so I get Na, NO3. And the Fe ends up with the OH. Now I need to know the charge. Well, that 3 was dropped and swapped from the iron. So Fe is 3 plus, OH is 1 minus. When I drop and swap, I get FeOH3. Oops, that's not a very good 3. I want to say, though, if you do not include those parentheses, it's impossible to balance. You'll spend forever on it. Okay? So that's a big clue. If you cannot balance something and you're going through it and you're getting numbers like 25 and 103 and really enormous numbers, that's when you stop and you go, wait a minute, I want to check my formulas again, because the formulas tell you so much about how to balance it. So I'm looking at this and I'm seeing 1 Na, 1 Na. I see 3 NO3, so I'll put a 3 here. That gives me 3 NOAs and 3 OHs. Okay, so you can interpret by reading the equation so much. You can figure out what kind of reaction it is. You can figure out what the charges are on a lot of things just by undropping and swapping, just like I did with the NO3 here down here. Okay, you can figure out how to figure out what the products are. You're looking for a solid. Well, this is a double replacement. Here, That's aqueous because all nitrates are aqueous, but most hydroxides are solids. And that's what you're looking for in a double replacement. So you have to pay attention to all the clues that are given to you. Cannot rush this. Do not jump to balancing fast. I know it's easy. I know you know how to do it. Take your time and get the formulas right first, then balance.